Okay, so let's take a look at this same problem. So the figure A shows a circuit that contains three identical resistors with resistance R to be 9 ohm, and then two identical inductors with inductance L to be 2 millihenry, and an ideal battery with EMF E equals 18 volt. What is the current I through the battery? Okay, I through the battery just after the switch is closed. So currently the switch is opened. Okay, so yeah, maybe for some time, okay, maybe let's say t equals 0 second, or the switch is closed. So just after the switch is closed, what will be the current of I? Okay, so before we need to know that we need to know originally, if the switch is closed, what is the current going through the whole circuit. Okay, so it is an easy question, because we won't have any current. Okay, so the current going through will be zero. The current going through will be zero. The current going through will be zero. Okay, so just after the switch is closed, okay, what will be the current? Okay, so just as what I mentioned, for the inductor, the current is continuous. Similar for this one. Okay, because the current for this inductor and the resistor should be the same. Okay, so this is these two elements is in series. Also, this R and this L are in series. So the current here should be therefore this R and this L should be the same. For this L, for this R should be the same. Okay, so just as what I mentioned, L, the current before the switch is closed is 0. So when the switch is when it is just after the switch is closed, the current of this inductor should also be 0, and so as this resistor. Okay, so we know that there won't be any current. There won't be any current going through this path. And similar for this one. Okay. This is due to the current of the inductor should be continuous. So which means when the switch is closed, there is only current going through the middle path. Okay. So in this case, I should be E over. Okay, so we just ignore this part. Okay, so the current is simplified to this. Okay, we only have a single resistor and then an E here. Okay, so we have an I. Okay, and then this path is disconnect. This path is also disconnect. Something like that. Okay, so we have E over R, which will be 18 over 9 ohm. Okay, so which is 2A, like this. Okay, so okay, so so for the question B, what is the current I going through the battery long after the switch has been closed? Okay, so in such a way, maybe we still need to go back to here, okay, to observe a bit. So in such a way, for when T is very large, then this term will turn to 0, because this is like a negative infinity over a constant. Okay, so exponential to negative infinity will be 0. So when T is very large, this term will be a 0. Which means this I will be a constant. Okay, just as actually it will be something similar to this. Okay, also for the I will be something like this. Okay, so it turns out to be it should be something like this. Okay, something like this. Yeah, because V equals IR. So yeah, although the scale is not the same, but the shape of this formula will be like that. Okay, so I will turns out to be a constant. What does it mean? Yeah, because VL will be L di dt. Okay, so if I turns out to be a constant, the V going across the inductor will be 0. Okay, so when T is very large, I will be a constant. I will be a constant, and then VL will be 0. This is easy to imagine because if the current is fixed, the B field generated by the inductor will be constant. So there won't be magnetic flux changing. So there won't be any induced EMF. Okay. So in that way, okay, this inductor will have a zero voltage across it. So which means here, when you need to consider the current I going through the battery long after, which means T is very large, or T tends to infinity. So in such a way, you will consider the voltage across this stuff will be a 0. This VL will be a 0. Okay, so it means you can regard it like this. Okay, we have a battery here. Okay, so for the middle path, you still have a R. Okay, nothing special. And then for the left part, this is an R, this is an R. Okay, nothing changed. But for this L, because it doesn't have any voltage drop or voltage difference. Okay, so you can consider something like this. Okay, so this L somehow disappear. As much as the current settle. 就是在它的电流不变之后它就再没有那个电压降再没有电压降，那你就可以把它看成是一个短路的状态。Okay, so in such a way, if you consider this 2L is a short circuit after a long time, so the circuit turns out to be 3 resistors in parallel. So the total resistance will be R equivalent to be R parallel R. So it turns out to be R over 3. Okay, so I here, for the I here, will be E over R equivalent, which will be 18 over, okay, so R over 3 will be 18 over 3, which is 6 ohm. Okay, so 18 over 6 ohm will be 3A. Sorry. This one should be 9. Okay, this one should be 9. So this one should be 3. This one should be 3. So this one should be 3, and this one should be 6. Okay, something like that. Okay, so this is okay. This one, and this one. Okay, so be something like this. Okay. So far, any questions? Yeah, because this is honestly speaking, this is related to the circuit theory. But in this course, it is like the circuit theory in ECE. They will have a whole semester to talk about the circuit theory, starting from the resistive circuit and then talk about the RC, RL, and RLC circuit for a whole semester. But in this course, okay, actually I think all the chapters are compact in 2 chapters, okay, like chapter 27 and 31, and then a little bit here, okay. So maybe you feel a bit difficult, yeah, because we don't have too much time to talk about it deeply, yeah. Yeah, because it is not a circuit course, it's just a physics course, so it just compact it in 2 chapters, yeah, and then try to go through all the topics, yeah. So actually for this, considering the initial condition already occupy a chapter, a whole chapter, yeah, within 9 or 10 chapters in a semester. Yeah. Okay, so here is another sample problem. So here it says a solenoid has an inductance of this value and a resistance. If the solenoid is connected to our battery, how long will the current take to reach half of its final equilibrium value? Okay, so so here, so we still need to a little bit talk about this tau L. Okay, here we have a tau L called the inductive time constant. The inductive time constant 就是一个叫做时间常数时间常数，这个时间常数是干嘛的？就是告诉你，对，时间常数就是告诉你说这个爬升的多快，这个爬升的多快，这个就是告诉你说这个 tau L 的话，就是过了这个 tau L 的时间，它就会爬升1的负1次方，或者乘以100%，它相当于多少呢？爬升了60几个，63.8%吧，好像是，我没有记错的话，大概是这样。你可以按一下计算机，就是2.7181881828分之一就是这个数2点几分之一嘛，哦不对，应该是0.368，这个是0.368应该是这个是0.368所以如果是1减去这个0.368的话，就是会多少啊？0.6320.63，很奇怪的我按一下计算机好了。e 的负1次方是多少啊？e 的负1的负1次对啊，0.368减1的话是0.632 ，OK， 所以这个是爬升到这个1减去这个相当于爬升了62.8%。你说这个数字有没有什么很大的意义吗？其实是还好，就是反正就是这个是1减1的负1次方那一般来说的话，我们工程上的话，就是如果这个时间远大于这个5倍的 time constant 的话，大于这个5倍的 time constant 的话，我们就假设说它会无限接近于这个最终的值，因为这个值怎么说？这个值是永远都不会零嘛，永远都不会零，但是如果它大的够大的，就比如说 e 的负5次方的话，它就会很接近零，你一般就可以忽略。看你的能够容忍的那个误差范围是多少5倍的话，一般来说肯定是够的因为这个 e 的负5次方是多少啊 ？e 的负5次方的话是0.6个点0.6%，所以是可以忽略的 所以就是有一个叫做 time constant 的东西，就是 time constant. So this is a time constant L over R, so which define how fast it will start from the beginning value to the 62.8% to the equilibrium point. Okay. So here it asks you how long it will take to reach half of its equilibrium value. So it is a little bit shorter than the time constant, but yeah, actually we know that IL will be like E over R and then 1 minus E to the negative T over tau L, something like this or something like this. Okay, so of course the steady state value should be this one, but we would like to know how long it will take to reach half of this equilibrium value. So which means we would like to know is what is t for this term to be 0.5. Okay, so we will have 1 minus exponential to t to minus t over tau L equals 0.5. Okay, so half of this equilibrium value. Okay, so we can move it to the left side, move this to the right side. So and then we take log on both sides. So we have or maybe we can take the reciprocal on both sides first. So we will have exponential to t over tau L equals 2. Okay, so move it to the left side, which is 1 minus 0.5, which is 0.5. Take the reciprocal will be 2. Okay, move it to the right side, take the reciprocal, the negative side become positive side. Okay, and then take the log on both sides. We will have t over tau L to be natural log of 2, and then move the tau L to the right side, something like this. Okay, so tau L will be L over R, natural log of 2. Okay, so it is actually 53 times 10 to the negative third power over 0.37 natural log of 2. So this is nothing but 0.1 second. 0.1 second. No. Okay. So here we talk about the energy stored in the B field. Okay. In chapter 25, we have talked about the energy stored in the E field as a capacitor. For a capacitor, it will generate E field, so energy is like stored in the E field. Okay, so here the inductance generate B field. Okay, so it's like the energy from the battery will store in the B field. Okay, generated by the inductor. Okay, so UB will be like half of Li square. So the derivation will be like dUB to be the P. Okay, which is IV. Okay, and then V will be L didt. Okay, so try to integrate on both sides. So integrate this stuff. Okay, dt cancel. Turns out to be half of Li square. Okay, so if you still remember, UE is half of CV square. Half of CV square. Okay, so所以它们也是一个对称的，就是状态，就是E field 的话就是 C 这是 L， 这是 B， 这是 I。 因为对于电容跟电感来说，它们的 V 跟 I 的角色有点兑换啊，有点兑换，就是这个式子的话，就是 I 在左边啊 ，V 在这里啊，电感的话就是 V 在这里，I 在那里啊，然后 C 换成 L 啊，所以那个式子也是类似的感觉啊，类似的感觉就是C 就换成 L，V 就换成 I， 那 UE 就换成 UB。Okay, so here we have another sample problem. So it says a solenoid has an inductance of the same value, resistance with the same value. So if a 12-volt EMF is applied across the coil, how much energy is stored in the B field after the current have built up to its equilibrium value? Equilibrium value. So for part A. So for part A, we have I equals E over R. Okay, so this will be the full current. Full current will be 12 over 0.35, which is 34.38. So this is the full current. Okay, so in that way, how much energy is stored in the B field? How much energy is stored in the B field? So the UB will be half of Li square. So half of 53 times 10 to negative third power and then times 34.3 square. So this is nothing but 31 joule. 31 joule. Okay, for part B, after how many time constant will half of this equilibrium energy be stored in the B field? Okay, so this is a little bit different from this one. Okay, so this is half of its current, this is half of the energy. Okay, so they are different here because the energy is proportional to the square of the current. Okay, so the condition of these two questions are not the same. Okay, so it is like UB half will be half of Li half square, which is half of Li square. Okay, so this is the original, the full power. Oh, so we need to take half of it. Okay, so here we would like to have a half of Li squared to see what is I half, what is the relationship between I half and I. And then the answer will be, okay, so some of them will be cancelled. So let's say this 1/2 will be cancelled, this L and L will be cancelled. So it turns out that this I half will be 1 over square root of 2i. Because here we have a square, so take the square root on both sides. We have a 1 over square root of 2 here. Okay, and then still we recall this I equals I and then 1 minus exponential 2 negative t over tau L. Okay, so here we would like to have exponential to negative t half over tau L to be or I should say 1 minus this one, 1 minus this one will be 1 over square root of 2, 1 over square root of 2. Yeah, which means we would like to have this I to be I half, so t will be t half. Okay, and then if I to be I half, it is actually 1 over square root of 2i, so I and I cancel. So it turns out to be 1 over square root of 2 here to be this term. So we can have exponential to negative t half over tau L will be 1 minus 1 over square root of 2. Okay, which is square root of 2 minus 1 over square root of 2. So finally, t half will be natural log of square root of 2 over square root of 2 minus 1. Yeah, because this is a negative side, we take the reciprocal, becomes a positive side. And then here we take up the reciprocal. And then we take natural log on both sides. So this thing comes out. So we have natural log of square root of 2 over square root of 2 minus 1. And then we move this to the other side. So we have a tau L here. Okay, so finally, we have a tau L, and then natural log of square root of 2. No. So actually, this one will be like, this one will be like 1.23 tau L. 1.23 tau L. For this one, we don't need to plug in the value to find the tau L because it just asks you how many time constant will blah 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 blah. So we just keep how many here and then time this time constant. So the answer will be So the answer will be 1.23 times like this. Okay, so so here we also would like to mention the energy stored in the B field. Yeah, but here we would like to consider the energy density. Okay, the energy density. Yeah, actually we also we also have it for the energy stored in the E field, the energy density, density in the E field. So this one is the energy density in the B field. Okay, so the energy density will be the energy itself, the energy in the B field divided by the volume. Okay, so here we just assume we have a solenoid, and then we have a cross-section area to be capital A, and then the length is L with a current I, something like this. So the volume, okay, yeah, the volume, yeah, for this one is like a cylinder, 就是一个圆柱体，所以就是截面面积乘以这个高度，所以就是 A 乘以 L，A times L here is the volume. And then UB will be half of Li squared. So 2 goes to here, and then Li squared, and then AL go to here. Okay, so here we try to slightly rearrange. So capital L over L go to here, and then I squared go to here, and then 2A go to here. And then previously in this chapter, we have capital L over L to be mu 0 n square A, like this, so that we can plug this one to here. And then for the solenoid, we also have B equals mu 0 I n. So we make use of these two. And then actually from this one, we can have I equals B over mu 0 small n. Okay, so we can plug this one to there. Okay, so UB will be first, this one will be this one. Okay, so we put this one to here, and then I square over 2A to here, and then I will be B over mu 0 n, so B over mu 0 n, and then whole square over 2A. So we can do some cancellation. A and A cancel, and then here we have n square, cancel with this n square. And then this mu0 partially cancel with this one, so that it has a mu0 in the numerator. Mu0 in the numerator. So finally, it turns out to be 2 mu0 in the denominator, and then b squared in the numerator. So this is ub equals b squared over 2 mu0. And then if you still remember, ue will be half of epsilon naught e squared. Okay, so this is also a duality. This is also a duality. So 1/2, this is also 1/2. Epsilon naught turns out to be 1 over mu naught, and then E turns into B. Okay, so we have this one for the energy density in the E field, and then this is the energy density in the B field. So yeah, so in chapter 33, when we talk about the electromagnetic wave 当我们讲这个电磁波的时候，我们会用到这两个式子的。Okay. So finally, in this chapter, we will talk about something called the mutual induction. Okay. Previously, we talked about the self-induction, 就是叫做自感应。那这个中文的话叫做互感应。互感应 ，mutual 嘛，就是互相的意思，互相的意思。简单来说，你可以把它想象成一个 transformer， 叫做变压器叫做变压器。Okay, so how do we understand it? Okay, so here we have two coils, just similar to the very beginning in this chapter. We have two experiments set up. One is with a magnetic bar to move, and then the other one we try to have the coil, and then at that time we only have a switch, but here we replace it as a tunable resistor, so that in this case, if we like to move the tip of this tunable resistor, so we can change the resistance, and so we can change the current. So if we can change the current, we can also change the B field generated by this coil. That's the idea. Okay, so here the idea is okay, so here is that the B field B1 produced by I1 in coil 1 extend through coil 2. 就是说，如果现在我们假设有两个圈我们有什么？我们有两个线圈。第一个线圈是 N1 个 N1 turn， 那第二个线圈是 N2 turn 它们就是这样。Okay, so now for the coil 1, okay, so this is the coil 1, we connected to a battery with a tunable resistance so that we can control I1 here. Okay, so if this I1 is changing, okay, this coil will generate a time-varying B field, okay. Yeah, so this B field will go through the coil 2, okay, so and then if this magnetic flux is also changing, okay, so yeah, so probably it will change, because if B1 is changing, the magnetic flux going through the coil 2 will also change. So in such a way, for the coil 2, according to Faraday's law, as much as it has a time-varying magnetic flux, then there will be induced EMF. So here we have an ammeter here, so that we can sense a current. There should be a induced current or induced EMF here. Okay, so now we doesn't change the coil. Okay, we still keep N1 here and N2 here, but now we connect the battery and the tunable resistance to coil 2, and then we connect the ammeter to coil 1. Okay. So in such a way, we can control the current for the coil 2, so as I2. So in that case, coil 2 will generate B field, time-varying B field. So the magnetic flux for coil 1 is also time varying, and then according to Faraday's law, it will also generate the induced current and also induced EMF. So this phenomenon, we call it the mutual inductance. Mutual inductance. So in such a way, it can be written as E2 equals Lm minus m di1 dt minus. So comparing with the previous one, which is already also, although I don't use it, but if we need to compare it here, so it will be like E equals negative L di dt. Okay, for that case, we don't have 1 and 2 because we only have a single coil. But here it means that if we try to control the current for the coil 1, in that case, we have a mutual inductance, 就是叫做互感值mutual inductance， 取代掉这个 L， 因为它这个是自感应自感。Okay, and then you will generate the EMF for the second coil, and then similarly with the same mutual inductance here, if we try to change the current for the coil 2, in that case it will generate induced EMF for the coil 1. Okay, so yeah, so this one, yeah, try to quantify the mutual inductance, or if you like to use V, so it will be nothing but V2 equals M di1 dt, or V1 equals M di2 dt, something like that. If you try to forget the EMF, it will be the same thing. Okay. Okay, so here we still have a sample problem, 30.8. Okay, so here it says the figure shows 2 circular closed pack coils, the smaller radius R2 with N2 turns. Okay, so it means this one. Okay, this one is smaller with N2 turns. Okay, connected to here with an ammeter. Okay, so yeah, so and then being coaxial 就是这个之前出现过，叫做同轴coaxial。同轴的意思是这两个都是圆柱体嘛，所以它中间有一根轴嘛，所以两个轴重合的话就是叫同轴嘛。With the larger radius R1 and N1 turn, okay, 所以大的那个是 N1 turn， 然后半径是 R1， 都是 R1 比较大的 ，N1 N2 就不知道谁大谁小了。And in the same plane, Okay, so for question A, derive an expression for the mutual inductance M of this arrangement of these 2 coils, assuming R1 is much larger than R2. Okay, so here we would like to find phi 21. Yeah, because here we will have for the coil 1 we have battery generate I1 here. Okay, so in that way this coil will generate a B field. So here we have B1, but the mutual inductance is occurred for the second coil. So for the cross-section area, we only consider the A2. Okay, so yeah, so originally we have N equals, originally we have L is N times phi B over I. Okay, so if we turn it into the mutual inductance version, it will be like M will be N2 and then phi 21 and then I1. Okay, so because the current or the B field is generated by I1, but we would like to consider the flux linkage for the coil 2. So this one is the magnetic flux for a single coil, okay, for the coil 2, and then multiply by the number of turns for the second coil. So it somehow makes sense. Okay, so it will be like N2 B1 A2. Okay, we just plug in this one here. Okay, over I1. Okay, and in chapter 29 for equation 29 and then 26, we have an equation like this: BZ equals mu 0 I R square over 2 times R square plus C square to the 3 over 2 power. So this is actually the B field generated by the magnetic dipole. B field generated by the magnetic dipole on the z-axis. Okay, so we just try to make use of it at z equals 0. Okay, because it mentioned that these two coils are on the same plane. So which means z will be 0. So in that case, we will have B1 to be N1 times B0 here. Okay, B0, which means that we swap z to be 0. Okay, so in that case, it turns out to be N1 and then mu 0 I, and then we should have R1 square. And then over 2. This one is R1 square to the 3 over 2 power, should be R1 cube. Okay, so it turns out to be N1 mu 0 I and then over 2 R1. Okay, because this R1 square and R1 cube can be partly cancelled. So this is B1. This is B1. So okay, so here we get the expression of B1, so we can plug it to here with this expression. So we have M equals N2 and then N1 mu 0 I. Yeah, this one should be I think it should be I1. This one should be I1. Okay, this one should be I1. I1 over 2 R1, and then A2 over I1. Okay, so we can do some cancellation. Actually, we can cancel this I1 with this I1. So finally, we get mu 0 N1 N2, and then A2 over 2 R1. Okay. And we also like to have A2 to be pi R2 square. Okay, so this is a circle. So the cross-section area for the second coil will be pi R2 square. Plugging it to here. So it turns out to be pi, put it in the front, and then we have mu 0 N1 N2, and then we have a R2 square over 2 R1. Okay, so this is the expression we would like to find. Okay, so bit. Yeah, so yeah, we can quickly finish this one. So for the second question, what is the value of m given this value? So which means we just need to plug in all the numbers in this expression. So pi mu 0 n 1 n 2 r2 square over 2 r1. So this is a pi, and then 4 pi times 10 to negative 7, and then times n1. N1 and N2 are all 1,200 square, and then R2 is 0.011, and then square over 2 times R1 is 15, 0.15, like this. So the answer will be 2.29 millihenry.